Hello everybody, and welcome to this short video on the introduction to an acid-base titration. So a titration is an analytical tool to figure out a concentration of a solute in a solution. And what we do is we use another compound that reacts with the solute compound of interest. And we'll also use, in a titration, a special instrument called a burette. Okay, so here's an example of a problem that can be solved using a titration. So let's say we have a solution of hydrochloric acid, but we don't know the concentration. Another word for concentration is molarity. So we have this hydrochloric acid solution, but we don't know the concentration of it. What we can do is we can actually use a compound that reacts with the hydrochloric acid, and we know that bases react with acids, so we can actually use a compound called sodium hydroxide, a strong base, to react with the hydrochloric acid. And this, what we're going to be able to do is we're going to be able to count basically the number of sodium hydroxide molecules that react with hydrochloric acid, and therefore by counting how many sodium hydroxide molecules we use, we can therefore count how many hydrochloric acid molecules we have, and therefore we can get to the molarity of hydrochloric acid. So on this slide, I just want to kind of go over some of the details about what's going on in an acid-base titration. And so in this particular example, what I have is I have hydrochloric acid down in this flask, so there's HCl, and it's aqueous HCl, and so aqueous means that it's in water and that it's soluble. So aqueous tells you something about that molecule in front of it. And so what that means is we put it in water and it's come apart. And how does an acid come apart? Well, it's going to release its hydrogen, and the remaining part of the molecule will exist as an anion, and these are going to be separate, floating around away from each other. And so when we put a hydrochloric acid molecule into water, so there's H2O, what's going to happen is it's going to fall apart. The hydrogen comes off as a hydrogen cation. We call those protons. And you're also going to have the remaining part, excuse me, that's wrong. You're going to have the remaining part of this molecule, which is a chloride. So you have these basically both of these species floating around in solution, and that's what's shown down there in the flask. Let's get some of this. So what we're going to do is we are going to take sodium hydroxide, and we know sodium hydroxide reacts with hydrochloric acid, and sodium hydroxide is very similar to hydrochloric acid in that when this is placed into water, it also comes apart into ions. And so this is going, when placed into water, so I'll write water up here. When this is placed into, sodium hydroxide is placed into water, the sodiums come away apart. Sodiums and the hydroxides come apart into these two ions. And so that's kind of what's represented in this drop here. So I have this aqueous solution. Let's see. Basically, I have this aqueous solution of sodium hydroxide, and I'm going to mix that with an aqueous solution of hydrochloric acid. And what's going to happen is the hydroxides in the sodium hydroxide solution are going to come in contact with these protons, or H plus ions from hydrochloric acid. When they do, they're going to form water. And so I've actually written that reaction down here. So hydrochloric acid, aqueous hydrochloric acid, plus aqueous sodium hydroxide is going to give you, from these hydroxides and that hydrogen, those are going to react with each other to form water. And so this is the balanced equation for the reaction between hydrochloric acid and sodium hydroxide. And this is just a graphical representation of what's going on inside that flask. Those hydroxides and those hydrogen cations, or protons, we call them, they're going to grab onto each other. And when they do, they're actually going to form liquid water. And the sodium ions and the chloride ions are just floating around, and those are what we call spectator ions. And so in this type of reaction, when you add a strong acid and a strong base, what's going to happen is you're going to form a salt. Right, so this is an ionic compound. Another name for an ionic compound is a salt, and you're going to form liquid water. That's an L. So back to the titration, and so why we're doing this. If we didn't know the concentration, and another name for concentration is molarity of the hydrochloric acid in this flask. So we don't know how many of these hydrogens floating around and how many of these chloride ions are floating around. What we could do is we could count how many sodium hydroxide molecules we drop into here. And if we have a way to indicate that we have dropped an equal number of hydroxides in this solution as there are hydrogen cations, if we have a way to say, hey, you've started dropping sodium hydroxide into the solution, and you've dropped enough to where there's equal amounts of sodium hydroxide and H+ ions, then by counting the number of hydroxides we put into the solution, if we can count those, let's say if we put 12 of those in there, that means that there's going to, at that certain point, that indicator point, there has to be 12 of these. So I'm not going to draw 12, but just pretend like this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12 hydrogen cations. And so if we know the concentration and we know how many hydroxides we're placing into the solution, and we know each one of those hydroxides reacts with one of those protons, if we have a way to show that there are equal numbers of hydroxides and protons at a certain point during this titration, we can then count exactly how many of the protons are in that solution. So here, in this particular example, we would have, we have two hydrogen cations, and so we'd actually have to drop 2 of these droplets, because each droplet in this particular cartoon contains 1 hydroxide. And each one of those hydroxides need to react with 1 hydrogen cation. Okay, but we don't ever do anything with on the scale of 1 to 2 or dozens or hundreds or thousands or even usually millions of atoms or ions. Are usually much larger, and we have to measure those in moles. And the moles, the number of moles that it takes to do this reaction is actually represented here in this balanced equation. For every 1 mole, there's an understood 1 here, 1 mole of hydrochloric acid, you need 1 mole of sodium hydroxide, and that'll give you 1 mole of sodium chloride and 1 mole of water. Okay, so the take-home message here is that we don't know how many of these cations are floating around, these hydrogens, but if we can count how many hydroxides we place in that solution to eventually equal that number of hydrogen cations and hydroxides, then we should be able to use the number that we counted here to extrapolate the number of cations that are floating around that solution. And that will answer our question of what is the molarity of the hydrochloric acid in solution. Okay, so what's important here is what tells us we're at the 1-to-1 ratio. We're at an equal amount of hydroxides to protons. Well, you have to have some type of indicator. And in the Chemistry 1141 labs, we use a color indicator that tells us when there's equal number of the hydrogen cations and hydroxides in our solution, and it actually turns a very faint pink. And the pink you see here is actually darker pink than what you'll see in the lab, or what you should see in the lab. Okay, so to actually do a titration, we're not just going to drop drops into a flask with the dropper. We're actually going to use a specific instrument, and this is called a burette. So this here is a burette, B-U-R-E-T, and those are expensive, so don't break them. What this is going to do is it's going to allow us to figure out how many hydroxides we're going to place in the solution to figure out how many protons are floating around in here. So we don't know how many of these protons are floating around. So we're going to use the number of hydroxides that we can measure using this burette. So in this burette, we're going to place the sodium hydroxide. And we know the concentration of this. You have to be given the concentration of this by your IA in the lab. Usually it's on the front of the bottle or carboy or whatever the stock solution is inside of the laboratory. So you have to have this information. All right, so once you get that information from whatever source, your IA or the bottle, you know the molarity of the sodium hydroxide. So that's our first known value. You're also going to be asked to get, I believe in your lab, it's 25 milliliters. Little m, large L. 25 milliliters of hydrochloric acid solution. You don't know the concentration, so you don't know the molarity, but you do know the volume. The volume is 25 milliliters. Okay, also into this flask is going to be your color indicator, and it's important that you put that in there. If you don't, what's going to happen is you'll never know when to stop. You'll never see a pink color. Remember, the pink color tells you when you have equal number of hydroxides to hydrogen cations. Okay, so what's going to happen here is you are going to turn this, so this little stopcock thing turns, all right, and when it twists, it's going to start allowing the sodium hydroxide that is placed inside of this burette to start dropping out, right? And you can adjust it to have a steady stream of whatever fluid is in that burette, or you can adjust it to just do drop-wise. And you'll see what I mean when you get into the lab and you start turning this little part. So in here, we have our hydrochloric acid in our flask. We have our indicator. We have sodium hydroxide up in this burette. We know the concentration. We know the volume of our hydrochloric acid down here. And what we're going to do is we're going to find out a third piece of information, and we're going to use those three pieces of information to find out a fourth. And I'll show you what I mean in just a minute. So once we turn this to release the sodium hydroxide into the flask, the volume is actually going to start going down. And this is going to be red starting at 0 and going to 50. And these are all in milliliters. Okay, and so at a certain point, what you're going to see when you start releasing the base into this acid solution is at some point it's going to turn pink, and it's going to stay pink. And you want a very light pink in this particular experiment. When that happens, you actually have your endpoint. All right, that's the endpoint, or what we call equivalence point of the titration. And that means that your hydroxides that you've put into that flask from the burette equals the number of cations. And if you know the number that you've dropped into that flask, and you know that one of these reacts with one of these, you should be able then to count the number of protons that are in that flask. And that's the goal. So once you see this pink color here, what you're going to want to do is you want to turn this stopcock to stop the flow of that solution. When you stop the flow of that solution, you can then read how many milliliters you've used. Right? So let's just go ahead and give some values here. So let's go back to the first piece of information. And let's just say that we're starting with 0.5 molar sodium hydroxide. That was on the bottle, or your IA gave you that information on the board. You know that you have 25 milliliters of hydrochloric acid in your flask. And let's say that we used 13 milliliters. So we went from 0 to 13. And this is red in milliliters. So you use 13 milliliters of sodium hydroxide. So I'll just write that 13 down here. Now you have 1, 2, 3 pieces of information. You have 2 volumes and a molarity. So now what we need to do first is you're going to have to convert milliliters to liters. And so we said we had 13 milliliters. Always convert that to liters. How do you do that? Well, you can do dimensional analysis where you say, okay, 13 milliliters, and I know from my lecture that I can convert milliliters directly to liters, and I know that I have to give the larger unit the value of 1 and define how many of those smaller ones I have in there. Milli stands for 1,000. So there's 1,000 milliliters in a liter. Milliliters cancels, you're left with liters. Do the math, you should get 0.13 liters. So this needs to be converted to liters first, 0.013 liters. So now we have 3 pieces of information ready to go. We have our initial molarity of our sodium hydroxide. We have our volume of our hydrochloric acid. This again is also going to have to change into liters. So we just do that now. We divide it by 1,000. And we have our volume of sodium hydroxide. So now we have 3 known values. We actually had to get the third value from the burette, but we have 3 pieces of the puzzle, but we need 4 to actually see the big picture. And what we're looking for here is what is the molarity. So what is the molarity of hydrochloric acid in that flask? We don't know that. We have no idea how many of these little H pluses are floating around in there. But using this 3 pieces of information, we can figure it out. Okay, so this slide looks a little bit busy, but I'm going to break it into pieces. All right, there's 1 piece, there's 2 pieces, and 3 pieces. And I have step 1, 2, and 3 here. So I'm going to get rid of those lines, but just you can pretend like they're still there. So the first step is in solving a titration between an acid and a base, or most titrations in general, is to start with the compound that you are given 2 pieces of information on. Now, if you remember, for sodium hydroxide, we were given both a molarity, 0.5, and a volume that we got from our burette, which was 13 milliliters, and I'll go ahead and convert that to liters, and 0.13 liters. We didn't know our concentration of, so this is sodium hydroxide, sorry, label that so you know what we're talking about. And then if we're talking about HCl, we did not know the molarity, but we did know a volume. We started with 0.025 liters. Okay, so we have 1, 2, 3, 4 pieces of information, and we need to figure out this third one using these. So the first thing you're going to do is you're going to turn to the sodium hydroxide. You're given 2 values for sodium hydroxide, and we're going to start with that, and then we'll use this piece later. So let me clear all that out of the way. So we said the initial concentration of sodium hydroxide was 0.5 molar. Remember, you got that from your IA, or it was on the bottle. We said that our volume from our burette was 13 milliliters. So this is the volume at the concentration that you use to get to the endpoint of the hydrochloric acid solution, which turned pink. So we're going to use these 2 pieces of information to get moles. Now, how do you get, if you have a molarity and a volume, how do you get moles? Well, there's an equation. This is the molarity equation, where molarity equals moles over volume, and the volume always has to be in liters. So we can use this equation to solve for, find the eraser real quick, sorry. We can use the eraser, we can use the molarity equation to solve for moles, because we're going to take this molarity of sodium hydroxide, this volume of sodium hydroxide, and we're going to be able to get from that moles of sodium hydroxide. How? We're going to plug these 2 pieces of information into this equation. But we're going to be solving for moles, and so this is our X we need to solve for. So we have to rearrange this equation. When you rearrange this equation for moles, it's going to be molarity times your volume in liters. Okay, we have molarity and a volume. So if you plug those two numbers in, the 0.5 molarity and your volume in liters, you're going to get 0.0065 moles. So we have actually taken these two pieces of information and figured out how many moles of sodium hydroxide. Now your next step is converting moles of sodium hydroxide to moles of hydrochloric acid. Whenever you need to convert moles of one compound to moles of another in a chemical reaction, you have to turn to the actual balanced equation from that chemical reaction. So what we're going to do is we're going to take that value that we got, 0.65 moles, and we're going to do what we call a mole ratio. And we're going to start this mole ratio off with the number from step 1, 0.0065 moles of sodium hydroxide. We want sodium hydroxide to go away, and we want moles of hydrochloric acid to come up. And so when you do that, this is your mole ratio. You can convert moles of sodium hydroxide to moles of hydrochloric acid. How do you do that? What is a mole ratio? Well, a mole ratio is simple. You're going to go look for the two compounds of interest. The two compounds are sodium hydroxide and hydrochloric acid. And you're going to say, what are my coefficients? Well, it just so happens in this balanced equation, the coefficients are 1 and 1. So we're going to set this mole ratio up so that moles of sodium hydroxide cancels, and we're left with moles of hydrochloric acid. We're going to plug in these numbers 1 and 1. They just so happen to both be 1 here. It's not always the case. If you do the math, you multiply 0.0065 times 1 divided by 1, you actually get the exact same number. So the number of hydrochloric acid, number of moles of hydrochloric acid is actually 0.0065 moles of HCl. Okay, so we've done actually 2 steps because we have moles of HCl. All right, first step was getting 2 moles of sodium hydroxide. Next step was getting 2 moles of hydrochloric acid. Then our final step is going to convert moles of hydrochloric acid to molarity of hydrochloric acid. How do we do that? We're going to turn back to the equation we used in the first part here, step 1, which is molarity equals moles over your volume, which is in liters. And we can simply plug in the moles of hydrochloric acid here. We can plug in the volume that we started with of hydrochloric acid here, and then we can simply solve for molarity by doing this division. Okay, so if we take that equation, moles of hydrochloric acid goes in my numerator, which is the top. This is my starting volume that was in the flask at the beginning of the titration. So we had something look like this. And we said, we don't know how many H pluses are down there. But we did know the volume, which was 25 mils, and we converted that to liters, and that is the number we see here, 0.025 liters. So we have our number of moles of hydrochloric acid, our volume of hydrochloric acid, and by doing this ratio, this comparison of this is how many particles of hydrochloric acid, this is my number of moles, my particle number, and this is my volume. What that does is it gives you a concentration, and another word for concentration is molarity. You do the math, the molarity of the hydrochloric acid is 0.26 molar HCl. How do we get that? By simply using information from a compound that reacts with the hydrochloric acid, which was sodium hydroxide in this example. Okay, so another way to calculate this is kind of a shortcut method that encompasses all 3 of those steps. So again, we have our 3 steps here. Our first step, we are multiplying molarity of sodium hydroxide and volume of sodium hydroxide. Then we're basically doing a division between the number of moles of each one of those. And then we're taking all that information and dividing by the volume of the acid. Well, if you look at the equation down below here, we have something that looks a little bit like the dilution equation, but it's a little bit different. So M stands for molarity, V stands for volume. What this is is the number of hydrogen cations. And the way I like to explain this is if we have the balanced equation of HCl plus NaOH gives us H NaCl plus water. That's an O. This H actually represents how many hydrogens you see that will come off of that molecule. One of those molecules releases one of those hydrogens. And this hydroxide in parentheses over here is going to be the number of hydroxides that you see come off that molecule. So if I have one HCl molecule, HCl, and I put this into water, I'm going to see one hydrogen come off. If I take the sodium hydroxide, put sodium hydroxide into water, I'm going to see one hydroxide come off. Okay, so in this particular example, in parentheses here, you would see a 1. I mean, one hydrogen came off that acid. A 1 here, that means one hydroxide came off that base. So this equation can be cut into sides. You have if you're doing an acid-base titration, you can call one side your acid side, and the other side is going to be your base side. Now, what we were trying to solve for was the molarity of our acid. And if this is our acid side, that's our molarity of our acid, M1. So if we wanted to solve for M1, what we'd have to do is divide both sides by the H plus concentration and the volume 1. That would cancel here and here, leave us with only M1 on this side. But we have to do this to this side as well. So we have our H plus over here and our volume 1 as well. And if you look where this arrow is pointing, I've actually rearranged that here. And what I want you to do is I want you to look at this equation and then look at our first step. What we did in our first step was multiply molarity times our volume for sodium hydroxide. Well, sodium hydroxide is our second half here, which is M2 and V2. Well, we're actually multiplying M2 and V2 in this equation. Then our next step was to basically compare the mole ratios, which is how many hydrogens and how many hydrogen cations, how many hydroxides react with each other. Well, that comparison is actually shown here. And then our last step was to take our number that we have thus far and divide it by our volume of our acid. Our volume of our acid is V1, and that's going to be our last step here. So all three of these, 1, 2, 3, are encompassed in this equation. And if you were to take all of the numbers here and plug them in and solve for M1, you would get the same concentration as if you had done this stepwise. So there's two options when you're solving an acid-base titration. You can do the long method, which kind of explains what's going on with this type of calculation. And that's typically what I teach in my classes. But I always introduce this shortcut method as well. Just remember that if you're taking lecture right now, the 1341 chemistry lecture, you're going to see an equation that looks like this. That's the dilution equation. That is different than the equation that encompasses the mole ratio, which is the number of protons compared to the number of hydroxides in this reaction. So keep that straight. Another thing to note when you're doing these calculations is your volumes always have to be converted to liters. Right? Okay, that wraps up the video. Hopefully this helps explain titrations a little bit, and you guys have a great day.